Hey, welcome to the shop. Laser welding has created quite a stir on the internet lately as equipment has gotten into the hands of more small shops and hobbyists. Comment sections have blown up with one side saying that those welds will never hold and it's just a scam, and others who say that this is the future of welding and it's going to replace all else with no skill required. Well, I know that the truth lies somewhere in between, and we're going to dive into that today. We're going to look at how laser welding works, what you can do with one of these smaller systems. We're using the X1 Pro from XLaserlab, and also some of the limitations of a system like that. So how does laser welding really work? Well, just like you'd use a high temperature flame with oxyacetylene or an electrical arc to locally melt your material, you use a beam of light. And the light is actually generated here inside the laser source, and it travels through this cable through fiber optics out the end here. Now that beam is so concentrated that you actually need to move it around, and so there's a little mechanism inside the gun that will actually wiggle the beam around to spread it out a little bit and do a really fast weave, so to say. When that laser beam interacts with the metal, it will melt it and join your pieces together, but you need to protect it from the atmosphere. And so there's actually a shielding gas that comes out of the end here, either argon or nitrogen, to protect that molten weld pool, just like you'd have with MIG or TIG welding. And if you need to add additional material, you can do that with wire. And so there's a wire feeder here that'll push extra material into your weld. So there are many of the fundamentals that are similar to other welding processes. You're really just using a different source of heat than an electrical arc or flame or something like that. Many people don't realize how well established laser welding is as a process. It was first developed in the 1960s and 70s, and I worked with laser welding for many years in my engineering career on both industrial, land-based gas turbine engines and jet engines for the aerospace industry. And last time you took a commercial flight or drove your car, your life depended on laser welds. What is new is the technology that gives you these smaller, more affordable packages that you can buy today. Let's take a look at the system. This is the XLaserlab X1 Pro. It's a 700 watt system. It's fully self-contained, so you don't need an external chiller because it's air cooled, and it can run off of a 120 or 240 volt outlet. Even the base package includes a wire feeder, and I was pretty surprised to see what's inside here. Has dual drive rolls, and it can actually accommodate 4 different sizes of wire with the extra rolls that it includes. It also comes with a whole bunch of accessories. You have your gun, you have replacement lenses, you also have all the different tips and consumables that you need, safety glasses, and a remote e-stop with a magnet on it. And these aren't a shade like a traditional welding helmet. They're engineered to actually block out a certain wavelength of light for the particular laser that you have. All the connections are here on the back, and it was straightforward except the gas connection is just a push lock fitting for 6mm tubing. I didn't have any of this, so I needed to pick up some tubing. Now let's take a look at the settings. The menus are actually really straightforward, and I think it's pretty well designed. You have welding, cutting, and cleaning. We'll look at cutting and cleaning a little later in the video, but right now let's focus on welding and click confirm. So right here are your main settings. You have a power, and then the swing frequency and swing width, or how fast and how far it actually oscillates that little beam. And how do you know what to set those to for a given material? Well, it's already programmed in here. So if you go to click on that preset button, I can select carbon steel. I can select 1mm thick, 2mm thick, 3, so that's like 1/8 of an inch. This is some 16 gauge stainless steel. And we're going to do an autogenous outside corner joint on this. Autogenous means that there's no filler metal. And this is a really common TIG weld to do if you're doing a lot of kitchen work or stainless like that. Or even there's some similar joints like this in custom automotive work. There's a tiny tack right on there. I have it on pulse mode, and I'm just manually controlling my travel speed here. Really easy because my distance is controlled just by resting right there on the edge. Hold some post flow there. And it's a nice clean bead. It's as consistent as I was on my travel speed. And right through there, I think I had it dialed, you know, just right to keep that color. And this doesn't have some kind of a big shielding cup to give your color. It's all from that low heat input. And I can grab this and pick it up right after it's done just with a thin TIG glove, which I wouldn't be able to do on a TIG welded part. So if I were doing a lot of kitchen work or stainless, things like that, I would much rather run this than run, you know, say a TIG welder on it. Now on the back side, there's a little sugaring because we didn't back purge, which is where you put shielding gas on the back side. But hopefully you can see it's clear that we had full penetration all the way through. Now I want to get an idea of the strength of this weld. The weakest part should be on the inside, and so I'm going to bend this up to try to break that root open. That's no gimmick right there. I mean, that's really good. There we go, bent all the way as flat as I can get it. Austenitic stainless steel. It's not showing any sign of cracking. Now, while this is an application where this machine really shines, it turned out to be a lot more capable than I expected. So let's go ahead and weld together some 1/8 inch or 3mm thick coupons with some filler metal on here. The wire feed installs just like this right here. Adjust it so it's sitting right like that. Make sure everything's tight. There are buttons on the wire feeder to manually feed or retract. So I can press that retract button and it'll just draw the wire back until it just barely hits that red laser indicator right there. I'll go ahead and tack this up. You know, being able to tack weld efficiently is pretty important for fabrication. Just like that. I had some sort of issue with my wire retract settings, so that wire got stuck in the puddle at the end. You can adjust that a little bit. That little weld is the definition of consistency, if you ask me. I mean, it is just beautiful, and it makes sense because the wire was pushing me along, so everything was controlled by the machine. It's basically an automatic process. Now, the actual fillet weld size is quite a bit smaller than you'd get with a MIG weld. Very difficult to get a weld that small. So I checked the leg length to the best of my ability here, and I got about 85 thousandths of an inch, which is right around 2 millimeters. And in a lot of applications, you know, if you're building furniture, if you're building handrail, things like that, that's going to be appropriate for 1/8 inch thick material structurally. And how nice would that be without any grinding or anything to have that appearance? But let's check and see what kind of penetration we got out of that weld and, you know, how strong it holds up. Just welded on one side. I've cut this cross section of the weld, and I'm going to put an acid etch on here. This should reveal where the actual weld penetrated down to. And this gives a snapshot in one area of the weld penetration. So I've marked the original corner of the joint and also put a line to indicate how deep it penetrated into that joint, and it's about halfway through the plate. So even though that weld is small, you have a large, what's called effective throat of the weld, or basically a lot of meat there holding it on because of how deep the weld penetrated. Now, a cross section like that is just a snapshot in one area. The other test that I'm going to perform here is a fillet weld break test. And that's where I bend this open. Now, most of the content I've seen with laser welds, they'll weld both sides and then bend it over and be excited that it didn't break. But the reality is, if you're bending from the face of a weld, it's unlikely to break. With a fillet weld break test, I actually would like it to break so that I can see the penetration all the way along. So I've only welded one side, and I'm going to bend it open from the root side. And how difficult that is to open is going to be somewhat indicative of the strength, but the more important thing to look at is whether you've consumed the edge of that joint all the way along the entire length. That's really what you're looking for in a fillet weld break test. Let's do it. All right, sometimes these can be difficult, but a tiny little weld like this on 1/8 inch, how hard can this be to pop? So that right there is holding up pretty good. You can see right here at the end, the root of that joint is opening up a little bit. But again, we're bending open this side that hasn't been welded at all. So this is really trying to open it up. Let's throw it in the vise and see if we can't finish it off so we can look inside of the broken weld. It is still holding on, bent all the way over on itself. I did not expect that. That's typically a pass for a fillet weld brake test. Not that this is, you know, to any sort of a standard or anything. All right, let's see if we can't pull it back open and get it to fail. That, something else. Failure occurred out of the material on this upper plate. You can see it penetrated just about halfway through the thickness of that plate all the way along the joint right here. So if you were to weld that on both sides, there's no way that that thing is coming apart. But even on one side, in most applications, you're gonna be totally good, especially if you're putting tubing on base plates, things like that. And with that tiny little weld, I mean, what a cool appearance to have for furniture, for handrails, for other kinds of automotive parts. Because you don't have to do any post-weld grinding or anything. It's just ready to roll. So pretty cool. This is some 16 gauge 1-inch square tubing that I use a ton for building carts and brackets and things like that. So I'm gonna weld this outside corner. I'm gonna weld this butt joint here on the face. It's a groove weld, and then a fillet weld here on this inside corner, all with the same setup here, because it's really not practical for me to change tips in between every section of this. Now, tying in the start and end of the bead is something I'm still learning on the laser system, but I'm getting better at it, and I think it can definitely be done. So the welds on this are still intact, and it failed here in the base metal. And I mean, I was beating on this pretty hard to get that to happen, and you had a lot of deformation up here before we ever got to that point. So I'm impressed with the welds. Right here, I can see that I could benefit from a little bit of practice on how to tie it in. You know, tying in the end of the weld is one of the most important things with any process, and I'm new to the handheld laser weld. Let's take a look at another fillet weld, but this time it'll be on a lap joint like this. That is clean and consistent, and it was lightning fast to run. Because laser welding can move so fast, it puts overall less heat into your material. So I could pick this up right after welding just with a light TIG glove, and you can see how much less heat tint you have than other processes. This is going to reduce distortion, it'll give you better mechanical properties, and just pretty sweet deal. For joints like this, if you do a lot of that, this thing's a great fit for it. Pretty impressive. Now we're going to try welding some aluminum. I'm going to start off with that same lap joint here and see what kind of result we get there. To be honest, I didn't expect much out of the aluminum welds, but that went in really smooth. I mean, that's just as good a result as I got with the carbon steel. Well, that came apart pretty easily and didn't deform the metal at all. And I think that's mainly because aluminum is just a softer alloy and this smaller fillet weld size isn't enough. Are there situations where a laser weld like this would be adequate on aluminum this thick? Yeah, I think there are. If you just needed to seal something, or if the loads are very low, or on signage or things like that. But in a lot of cases, I don't see this replacing my TIG welder just yet for this thickness when I do have any kind of significant load. Now I'm going to try the same thing on a T-joint here and see if I get any different result. Yeah, pretty much the same thing, just too small to hold much of a load. Now I am curious, if I were to run a multi-pass weld and really build up that fillet, could I get the strength that I need on this 1/8 inch thick material? I'm gonna go ahead and run 3 passes and see how that does. All right, well that was pretty quick to do, 3 passes. This is pretty toasty here. And it's just as clean of a result. It's a little bit bigger, it's still not huge, but let's see what happens. Just like all the others, it's welded on just one side and I'm bending it open from the root for more or less a worst case scenario. Certainly a whole lot better, but once again, that fillet weld is just kind of small for aluminum. Is this going to be acceptable? Well, it depends on what you're doing. You know, in a lot of cases, even the single pass would be just fine, but in other cases it wouldn't. It depends a lot on the loading, it depends on the design of your product. Now, while it didn't hold much load with that 1/8 inch aluminum, I wonder if it'd work pretty good for 1/16 inch. This stuff's kind of a pain to TIG weld, and it could be a good replacement there. Let's give it a try. And now that looks nice. There's no other way to get a little bead like that on aluminum. You know, on steel, you can get a pretty small bead with a TIG welder if you're pretty good at it. But here on aluminum, I mean, pretty impressive on the 16 gauge. And you can see that it was getting through to the bottom there. I do have a little bit of distortion. Unlike that thick aluminum, which just didn't have enough weld size, this thin aluminum held up really well and bent clear over. I mean, we had just about the same size fillet weld, and it seems to be adequate for this thinner material. So this could be a real game changer. I can think of a ton of projects where I would pick this over TIG welding on this thin aluminum sheet metal. Let's go ahead and switch this over to the cleaning mode and try that out. I mean, if you don't think that's cool, you better check your pulse, because that is, I mean, pretty slick. Now, it does leave a little bit of a texture to it, so be aware of that. You can see it's eaten into the material. I don't know if I reduce the power, if I can get rid of that. Let me try that out. Yeah, that seems to be better. That's running 20% power right there. Look at that. Rust and mill scale gone in one quick step. All right, now let's switch this over to try out cutting. And saying you need to use an angle so it doesn't fire stuff back up into the gun. Cut quality is not bad for a handheld process. It definitely works. If you look down here on the floor, all of those burn marks are from the laser proceeding past my material. So you could shoot a hole through your foot with this thing, or create a fire, damage some stuff. You got to be really careful where it's pointed and what's behind it and where it could reflect. At the end of the day, what's the truth about laser welding with one of these little systems? Well, in a lot of ways it's awesome, and it has some limitations. Some of the things that are great about it are, one, those tiny little fillet welds are just beautiful. No post finishing needed, and it required very, very little skill to be able to do that. I learned it really, really fast. Also, those small fillet welds with the penetration that you got were insanely strong for the small size of welds. So that was a huge advantage, and the fast travel speed is going to reduce heat input and help to avoid distortion. The built-in cutting and cleaning modes are a real bonus, though I didn't really like cutting with this style of gun compared to a plasma cutter. It just felt sort of bulky and awkward. It wasn't really designed for that, but it does work. And you also need to be especially careful what's underneath, because not only do you have hot sparks, you also have that laser beam going past it. Another big advantage is the dual voltage, right? I did all of this running on a regular 120 volt outlet. I mean, that kind of blows my mind right there. Some of the limitations of this machine are, one, you're limited on your fillet weld size. So as you get into thicker material, it's just not gonna be adequate, at least not in any practical way. So we were great up to 1/8 inch or 3mm thick material today on steel, and stainless steel would be the same with aluminum. You're starting to push it at that thickness, at least as far as getting a large enough fillet weld. The weld was good, it was just pretty small, and so that strength may be adequate for some applications and not for others, but on thin aluminum, it was great. Another limitation is just the overall size of the gun. With the wire feeder on here, this takes up a lot of real estate, and because it oscillates back and forth, it has to be aligned perpendicular to your joint. You can't twist it or anything like that. And so that could be a big limitation in certain situations, right? If you're doing some automotive fabrication, like building in a roll cage, it's gonna be very difficult to fit this in there in a lot of the spaces. Also, safety is a major consideration with this, because you can actually shoot your energy far away, clear across the room. So I wouldn't recommend working in a space that you share with someone else using a system like this, and you have to be extremely aware and careful. Now, as far as price, these still are not cheap, but it is a fraction of what you'd have paid, like 10% of what you'd have paid 5 or 6 years ago for similar capability. So that is insanely cool. It's around the same price as a good quality TIG welder, and you can save a bit of money off of that using the discount code I have in the description. Now let me know what questions you have in the comments, because I'm going to make 2 more videos over the next couple weeks where I'll actually dive into this specifically compared to MIG and TIG welding to see what's the best fit for different applications. And I'm also going to build a full fabrication project with all of the laser welding done using this, so we can see some of the ins and outs of actual practical use and fabrication with it. If you want to learn more about the system, be sure to use the link in the description and the discount code there. It helps you out, it helps me out here on the channel too. And if you enjoyed this or learned something, let me know by hitting that thumbs up or leaving me a comment, and we'll see you next time.